Sorry for the delay. I'm Peter Dueben. I'm going to talk about machine learning for weather forecasts. And I'm the coordinator for machine learning and AI activities at the European Weather Center for medium-range weather forecasts, which is kind of strange acronym ECMWF. And before I'm going to talk about machine learning, I just have one slide talking about ECMWF to just lay the scene and tell you what we do and what we are. We are a research institute, but we also generate 24/7 operational weather forecasts. And in particular, we are focusing on the medium range, on monthly and seasonal predictions. So we have global forecast models, and we're running particular kind of predictions a couple of days into the future. We are an independent intergovernmental organization, and we have 34 member states who are supporting us, that you can see on the right. We're based close to London in a town called Reading in the UK, and this means that I have already afternoon and not morning. And we have something like 350 members of staff in principle. And doing weather forecasts, we also have 2 supercomputers on site that are quite big. And we also obviously have a forecast model, which is the so-called integrated forecast system, which is probably one of the best weather forecast models for global weather predictions in the world. So that's us. And now coming to machine learning in particular, the question is obviously, why would machine learning help with weather predictions in principle, right? And to answer this question, I just want to kind of say a couple of words about the problems that we face when we want to make weather and climate predictions. So as you know, it's not very easy to do this. And if you ever trusted a 10-day weather forecast, you will know that it's not perfect. And the reason why this is the case is, first of all, because the Earth is so big. So if you see the picture on the right, you see just a very big planet. And our resolution in our models is very limited. So we have something like a 10-kilometer grid space in weather forecasts. And this means that a lot of processes, for example, individual clouds, are not really represented explicitly and correctly. And also, the Earth system is very chaotic. So basically, the atmosphere and ocean show turbulent behavior. But there's also nonlinear behavior in all of the other model components. And there are a couple of them. For example, the land surface, the cloud physics, atmospheric chemistry, and so on and so forth. So basically, and the last point is also that some of the processes that are important are not really well understood. So we also don't really have a very good working theory for all of those components. So kind of the bottom line is it's a very large and very complex system that shows nonlinear behavior. However, on the other side, we have a huge number of observations. Just to give you an impression, ECMWF is getting hundreds of millions of observations onto the site every day. So the observations come from satellites, planes, ships, ground measurements, balloons, and whatnot. So there's really like a huge amount of observations that has been kind of gathered in the last couple of decades. And also, if you kind of count model simulations in climate modeling, we're really talking about hundreds of petabytes of data. So if you combine those 2 points now, that we have a very complex system and we also have a lot of data, you will see that there's obviously a lot of potential application areas for machine learning in weather modeling. So there are many application areas for machine learning throughout the workflow of numerical weather predictions. And obviously, it's also true that since we have a high-performance computing center, we also need to think about what the future of high-performance computing will look like. And there it's also clear that machine learning will provide a lot of opportunities in terms of efficiency increases that we have in our system. So this slide is now basically to just kind of illustrate this point once more, that the machine learning applications are really spread over the entire workflow of weather prediction. So what you see here is our workflow where we get observations into our site, and we perform a step called data assimilation, where we basically fuse the observations with our forecast models to generate initial conditions. And then we have the numerical weather forecast, where we run our forecast and model into the future, kind of really look into the future. And then at the last point, we have post-processing and dissemination, where we kind of take the data that comes out of our model and kind of post-process it in a way that is usable by users. And if we now think about the different application areas for machine learning, you can come up with a list like this, which is very long and very detailed. So I'm not going to read it out or go anyway into the details. But you will see that it's color-coded, where the color is kind of referring to the different boxes in our workflow. And this is just to illustrate how many different application areas there are that could potentially actually make a difference. And the state of play at the moment is really that we know about those interesting application areas. and that we really have to kind of now investigate where deep learning and machine learning will actually kind of be able to be better than the state of the art. So we really are in the stage where we are exploring those different application areas at the moment. And what I'm going to do today in this talk is that I'm going to present a couple of example applications for machine learning that we are kind of looking into at ECMWF. And at the end of the talk, I'm going to name a couple of challenges that we're facing when using machine learning today. So I'm going to go through the workflow with my application areas. So first of all, I'm going to start on the left with observations. And basically, I'm going to start with an application that Ruth and Francesca at ECMWF looked into, where they basically try to kind of detect the risk for ignition of wildfires all over the globe. So what they've done, they basically look into 15 variables that they think that they're important to kind of detect a risk for ignition of wildfires. And then they also look into the satellite product. They can actually kind of see those wildfires appearing as you kind of, look into the satellite data. And then they generated the data set with 12,000 points. And basically, they use decision trees to kind of really understand whether they can map those 15 input variables to this kind of the fact whether there has been a wildfire or not, to kind of make predictions in the future. And the best classifiers that they get have something like an accuracy of 77%, which doesn't sound too great in principle. However, if you think about that, you will be able to predict a wildfire at this kind of level of accuracy, that's quite good, right? Even if you have sometimes a false positive, it's still a good prediction. And if you think about the ignorance matrix, it's plotted on the left, where you basically plot the true level against the predicted level. What you hope for is that most of the points will lie in the diagonal, which is definitely the case here, and less points are going to lie on the off diagonal to make this prediction useful. So that's one example. The second example is now in the second box of the workflow, which is data dissemination. And what we do here is that we try to bias correct the forecast model in the data assimilation system, and then at ECMWF we're using a very special system which is called 40VAR. So we basically now blend observations with a forecast model to generate initial conditions. And to do this process successfully, this requires an estimate of the error and an estimate of both the observations and the forecast model. To get an estimate of the observations is kind of doable. However, to get a good estimate for the forecast model is very difficult, and we don't really know how to do this at the moment. But we're now looking into something which is called weak constraint 40VAR, which is kind of an algorithm that would be able to take to learn this kind of forecast error as the error of the forecast model to correct it in the data assimilation process. And in particular, we're interested to kind of do this very high up in the atmosphere because we know that we have clear biases for temperature high up in the atmosphere. So we learn basically the bias, and then once we have learned the bias, we can correct the bias of the forecast model by just adding forcing terms to the system. And you can see in the figure on the right basically how this is working. So this is now an assimilation cycle starting in October 2018, going all the way to May 2019. And as kind of the cycle is proceeding, basically the error is learned. And this, you can see this in the figure because the color is bluish on the left side, dark bluish on the left side, and it's getting brighter to the right side, which basically means that the error is decreasing. So really, we can improve our data assimilation system by learning this model error using the reconstrained 40VAR here. This is still fairly simplistic in terms of the machine learning methods that are used, so not using deep learning yet, for example. However, we've now started a collaboration with NVIDIA to also kind of look into more sophisticated machine learning tools to kind of learn this forecast error to improve data assimilation. The next step is now the numerical weather forecast, and that's close to my heart, so you're going to see a couple of examples here. And one of the things that we are looking into is the emulation of different parameterization schemes, and in particular the radiation. The radiation is basically representing solar radiation coming in and then interacting with clouds going all the way to the ground, and then thermal radiation coming from the ground going up, again interacting with the clouds. And radiation is obviously very important for the energy budget of the atmosphere. And what we do now is that we run our forecast model and we store input and output pairs of the radiation scheme as we have it in our system. And we use this data to train a neural network. And once you've trained a neural network, you can actually kind of replace the radiation scheme, the original one, in the forecast model with a neural network and run the model again. Why would you do this? Basically, there are two reasons. First of all, it's very, very likely that the machine learning emulator is going to be much more efficient than the conventional scheme. And second of all, it's also going to be much more portable, right? Basically, it's very difficult to port our Fortran code that we have onto heterogeneous hardware, for example, GPUs and others. But once we can represent this by a deep neural network, we can basically port it to whatever hardware we want to. So these are some results. This is the surface downward solar radiation that we get. One of them is for the neural network emulator, and the other one is for the conventional scheme. We used REST networks here. And basically, you can't see big differences, which is good. And I'm also not going to tell you which one is which. So basically, we're getting good results in terms of the quality. And we also getting good results in terms of the speed up. So we get something like a factor of 10 speed up. I don't quote exact numbers here because our comparison is still not perfect, because we're still comparing like high-end CPU nodes with the original scheme against CPU calculations of the neural network. However, I'm quite confident that we will actually kind of be much better than a factor of 10 in principle. The other thing that I would still need to kind of say is basically yes. So we still like the very thing. And I also should mention that there are other papers in the done very similar steps for other permutation schemes and also radiation before. So this is really an active area of research. The second example that I want to give you is, again, the emulation of a scheme, which is now the gravity wave track. So we do exactly the same approach again. We emulate the gravity wave track using neural networks. And there are two different ways. And gravity wave track is basically the interaction of orography and kind of surface roughness with winds, and then you kind of you burn off very large scale waves that are difficult to represent on a coarse resolution grid. Therefore, you have to parameterize some of those. And the permutation scheme is now has one part which is so-called non-orographic and one which is orographic, which is directly linked to topography. And this is a collaboration now going on with Matthew Chantry and in Oxford. And again, we get good results. So the forcing from the original scheme is visible on the left. The forcing from the neural network is visible on the right, and you see the difference in the middle. So you can be convinced basically that the forcing looks good. It's now also possible to make a nice relation between the network size and the accuracy that we get. So on the plots on the right, you basically now see the mean squared error on a logarithmic scale plotted against the number of floating point operations that we have in our machine learning solution. And what you see is basically the axis here that draw a linear relationship in a logarithmic plot. So it's something like a power law, really. And you really see the increased complexity of the neural network towards the right and the errors decreasing, which you want to see. The only kind of sobering information about this plot is basically that the dotted and the dashed line are meeting in the middle. And this is actually kind of the cost and complexity of the original scheme. And you will see that it's slightly lower than the cross that we get from the neural network. Obviously, computational cost is not really well described by the number of floating point operations. So I'm still confident that we kind of faster with the emulator, but still we would have hoped that this cost would be kind of much lower down and lower and below the dotted line here. So basically, it's still questionable whether computational performance is going to be so much better than the neural network. And also, our results for the orographic wave track scheme are still not so as good as for the non-orographic scheme. So they're basically still work in progress to really get into results for those emulators. Let's go one step further. I appreciate this. Can you hear me? Yes. There's some background noise, but I'm still going to continue. I appreciate this is a very technical slide. I'm sorry about this, but I'm quite excited by this study. So I'm going to still show it to you guys. So what we do here is now that we try to precondition a linear solver. And a linear solver is a very expensive component if you're using so-called semi-implicit time-stepping schemes to use for some of the atmosphere and ocean models. And the solver really kind of takes up most of the expense of a forecast model. And the solver efficiency depends critically on what we call a preconditioner, which is basically trying to approximate the inverse of a very large matrix. And there's no good theory how to kind of build those preconditioners. So the question is, can we use machine learning actually for preconditioning and predict the inverse of the matrix using neural networks? and then reduce the number of iterations that the solver would require, and therefore reduce computational costs. And that's a study done together with Jan Ackman, Piotr Smolakevich, and Tim Palmer from Oxford and NCAR. And our test bed is now a global shallow water model. It's like a two-dimensional turbulence model on a 5-degree resolution grid, working with real-world topography. The method that we're using is really that we use a neural network to train to kind of predict the tendencies of the full time step given a model state. That's really trying to kind of basically do the time stepping for us. And this will give us an approximation of this inverse of the matrix. And then we will be able to kind of, hopefully we'll be able to reduce the number of iterations. And what you see here is now machine learning precondition are working on the left, and the normal standard solution that we would have, the implicit Richardson precondition on the right. And you see the arrow on the y-axis as you kind of do solver iterations. So if you kind of do more and more iterations, the arrow goes down. And the horizontal black line now is our line where we basically say, okay, it's good enough now. You can stop the solver iterations. And you see that the machine learning preconditioner is using around 7 iterations, whereas the standard model is using something like 4 iterations. So the preconditioner is not as efficient to kind of bring the number of iterations down as the implicit Richardson preconditioner. However, it's much more cheaper than the implicit Richardson. So again, if you just compare the number of floating point operations that you would require for the left and the right, the machine learning would actually kind of be on par with the implicit Richardson. So that's very exciting actually for us. And also, so the process is working and it's cheap. It's also interpretable because our machine learning solution is very simplistic and it turns out we don't need deep learning. We can use just a shallow network. And so we can actually understand what the scheme is doing. And it's also easy to implement even if you have no preconditioner in place. Now we go to post-processing and dissemination. So basically, that's the last box of our workflow. And the idea here is that we kind of try to correct the spread of ensemble predictions. So in numerical weather predictions, we often use ensemble methods. So if you kind of start from initial conditions and you run a forecast, you do not only kind of run a single model trajectory, but you try to run like something like 20, for example, and then as a result, you will get a probability distribution of the prediction that you make at the end. And this is very useful if you, for example, not only want to know the temperature in a week from now, but also whether you want what is the probability that the temperature is going to be below 0 degrees, for example, at this point in time, which is very useful for the user. And what we do now is basically that we investigate whether we can correct the ensemble spread calculated from a small number of ensembles via deep learning. And this is a collaboration with a group of Thorsten Höfler from ETH. And basically, it's using now 3-dimensional fields of a small number of ensemble members as input. It's trying to predict the ensemble spread for temperature at 850 hectopascal, so closest to the surface, 1 day into the forecast. And it's going to predict the spread of a 10-member ensemble. And this study focused initially on an area over Europe, so the results I'm going to show you are over Europe, but basically now we're kind of doing the same thing for global training. And now with global data sets, we're really talking about high-performance computing applications with terabytes of training data. So we're now in the process of kind of writing up the results for the global simulations, but I'm still going to show you results from the European simulations. And we basically use like a standard UNet structures for neural networks, 3-dimensional fields coming in and kind of 2-dimensional fields going out. So I was just talking about this application basically where we tried to build a forecast model without any knowledge about how to build a forecast model, but really just using machine learning and to kind of make a prediction system. And I told you that I retrieved data from ERA 5, so we bring out this data. And then I'm basically now trying to kind of learn the update from one time step to the next. And I'm going to basically build a prediction model out of this. And for this, no physical understanding is really required. And it turns out it's actually working quite well. So if you kind of see the videos now on the top, one of them is basically the analysis data, and the other one is my machine learning solution. And you will see that the features are exactly represented as you want this to be represented. So the network is picking up the dynamics very nicely. Also, in terms of the forecast error, if you compare like with like, the network forecast in the coarse resolution model, like a very, very coarse resolution model, like a model that we would have used 30 years ago, the forecast error actually looks very, very similar. So the question is this now the future? And I have to say it's probably not. And first of all, the simulations are unstable, so they're going to kind of blow up at one point. And second of all, it's also unknown how to increase complexity at this stage. So we only have one field here. If we would have 10 fields, it would be kind of, we wouldn't really know how to kind of make this stable then. And also there are only 40 years of data available. Even though we have an enormous amount of data in principle, we only have like 40 years of independent weather situation that we can use. So it's kind of unlikely that this is going to fly and basically kind of beat operational forecast at one point. However, having said this, there are now a number of papers coming out and already came out where people are looking into this in a much more complicated way than we have done with kind of really sophisticated convolutional networks and LSTM techniques and whatnot. And they get actually quite good results, so who knows? So the main challenge for machine learning in the community that we're facing at the moment is basically that we need to prove now that machine learning solutions can really be better than conventional tools. We need to do this in the next couple of years. And it's going to be a tricky exercise, and I'm going to skip here a couple of information. Basically also because the weather and climate sciences as such are very conservative. So it's not totally easy to kind of drag the entire community with you as you look into machine learning applications and their benefits. Why is this the case? So why is it actually quite hard to beat conventional tools? This is just a model, a slide that shows you a model simulation on one side and the satellite simulation on the other side for a model simulation at 1.45 kilometer resolution globally, which is kind of the cutting edge of what we can work with. So this would be run on Stein, for example, but we also have an inside ground where we run those simulations on Summit. And you will see that there's an enormous amount of detail in those simulations, right? So basically saying that we're not starting from scratch, even though we have all those problems with our models, it is actually kind of quite hard to beat an operational weather forecast model right now because it's very complex and it's kind of representing all of those different model components. And I'm going to skip this slide because it would take me too much time. Basically, the slides wanted to show you that if you make a model change, for example, for the Arctic, it may well be that you get a feedback which is negative over the tropics. So it's actually kind of this complexity of the system and the linking between the different system components basically means that it's very hard to kind of build new components without screwing up others. The real-world models show complex feedbacks in a number of time scales. The changes to the models require thorough testing, whatever you do, and this means significant HPC resources. And it's also difficult to compare computational speed for machine learning and conventional methods in a fair way. So what are the scientific challenges that we are then facing with machine learning? Basically, there's no reason not to use black box approaches within weather and climate models. However, there are a couple of problems that you need to think about. For example, it is quite unclear how to project our knowledge about the Earth system into machine learning tools as such. So how can we build like very customized neural network structures, for example, that would take into account the differential equations that we know? How can we diagnose the physical knowledge from the machine learning tools? How can we remove errors if we see them? And also secure things like conservation properties, which are really important to kind of drag the community with you, because otherwise a lot of scientists won't believe in what you say. How can we guarantee reproducibility if we want to use something like a deep neural network in operational forecasts? How can we find the optimal hyperparameter settings? Obviously, this is kind of, there's also, as we kind of gain experience, we will be able to kind of answer this question at one point, but it's still kind of a bit of a drag at the moment. How can we really scale the machine and improve efficiency on high-performance computing applications that basically take into account three-dimensional atmosphere fields on unstructured grids? How can we interface machine learning tools with conventional tools? That's more complicated than you may think. How can we design good training data in principle? And also, how can we explore the full phase space of the models during training? If you, for example, have climate change and the underlying system is going to change, so you would need to take care of this one way or the other if you want to use those tools. So many scientists are working on these challenges as we speak, and I'm sure we will have an enormous amount of progress in the next couple of years, but still these questions are still there to be looked at. Challenges for ECMWF in particular, obviously we will need to prepare for a lot of different data accesses from users. So if user wants to use our data that we basically provide for machine learning, they're going to request a lot of data. So this is going to change our kind of the request structure, which is quite a challenge for us. We will need to keep up with developments in supercomputing hardware to kind of really take care that machine learning is also kind of, well, that we can make the best out of co-design hardware for machine learning. We will need to support the community infrastructure for machine learning. And basically, we're doing our homework. So we're kind of now working on a very, very large cloud structure that we're developing together with ECMWF, which is called the European Weather Cloud, where I'm sure that it's going to be very, very useful for machine learning applications in the future. We're also having a workshop at ECMWF in October, and hopefully this is not virtual, but if it's virtual, then that's the way it is, on machine learning in the Earth system observations and predictions. And we also now introduce a special seminar series on machine learning that will start actually next week. My personal vision how machine learning should proceed in the future. Basically, I think we should kind of have a mixture of a top-down and a bottom-up approach to link machine learning with weather and climate models. So what I would suggest is to really study idealized equations and how we can, for example, get conservation properties into the system based on very, very simple equations. So that's really like research. We should also think about uncertainty because there are games machine learning here in terms of weather predictions. And if you kind of think about more of the top-down approach, we need to think really and start early to get scalable solutions, be able to kind of use machine learning within our prediction workflow as soon as possible. And they should take into account three-dimensional fields on the sphere on unstructured grids. And also, we should, as a community, build up benchmark problems similar to ImageNet, basically summarizing the big challenges that we have in our community. We make quantitative comparisons between different machine learning solutions. And we have done the first step here. So we have published the first weather benchmark tests for kind of the prediction of weather forecasts. And the focus should really be on useful tools for us that can serve as a beacon for the community to really drag the entire community with us. And I believe that we will need to show very, very soon that those beacons are useful. And on the other hand, it will be very hard work, and it will require machine learning solutions that are also customized for weather and climate models. I'm pretty sure about this. So what will machine learning for numerical weather predictions look like in 10 years from now? This is kind of a question I'm asked quite often, but it's very difficult to answer. So you have like a large scale here, where it could be that machine learning will have no long-term effect whatsoever, and that it's just a wave going through. But on the other hand, it could well be that the machine learning tools will actually replace almost all conventional models that we're working with. And a lot of senior scientists would actually say we are on the left side here, and a lot of senior scientists would say we are on the right side here. And it's very difficult now to judge where we are on the scale. So the error bar is still very, very large, which is unfortunate, but it's also exciting because then we can kind of try to get this error range down in the next couple of years. I'm going to skip this one. This is basically just showing that we can, in principle, also use machine learning co-designed hardware for atmospheric applications without using machine learning as such. What we've done here is that we replaced a very expensive kernel, which is so-called a Johnson transformation, basically doing matrix multiplications by half-precision matrix multiplications. And then if you think about it, you can actually use hardware structures such as the tensor core from NVIDIA and really get the entire speed up that you get for dense linear algebra with half-precision on those machine learning accelerators. And the forecast results look quite good. So this is a paper that has been published last year at the PAS conference and actually got the best paper award there. And I think there's more examples to follow to kind of show that we can also use machine learning hardware for conventional modeling. So these are my conclusion slides. I'm not going to read them out loud, and they're kind of kept very general. And at this stage, I'm left to kind of say thank you for your attention.
Great, thank you, Peter. You know, I do have one quick question. You know, with the constant inflow of data, will the AI continue to get better at forecasting as time goes on?
You mean when more data comes in and you can basically learn more? Yes, of course. I mean, basically, it really depends on what questions you want to look into. If you look into local questions, like really local weather phenomena, for example, there are a lot of independent local phenomena at the moment already, because the Earth is very big, right? So you have a lot of independent locations actually to train from. If you want to do like more on global predictions, it's really, really useful to get more and more data in and to kind of really understand more kind of independent situations, because you only have one global situation at a time, right?